Okay, Calc 2 people, moving right along. Let's talk about linear differential equations today. In particular, first order linear differential equations. A first order linear differential equation is a differential equation that can be put into this form: the derivative of a function plus p of x times the function equals q of x. Where y is our unknown function, p of x is just any function that behaves nicely on the interval of interest times the function we're looking for, y, and then another function of exclusively x. So where p and q are continuous on the given interval, if one is given, or the interval of interest. If we can set up a differential equation into this form, we can derive a solution, a general solution. In order to derive the general solution, well, here we're going to do it, and then we're going to do some examples. We have to find a function. I'm going to call it I of x. It's called the integrating factor for this function, and thus the I. Right? It's a magical function that's going to help us derive a template for the solution to a differential equation that we can put into this form. So in order to, once we find this function I of x, and I'll show you how to find it in a moment, we're going to take our differential equation, and we're going to multiply both sides of the equation by this great magical function I of x. So we'll have the product of two functions here times the function that we're looking for equals this integrating factor times the function of x on the right hand side of the equation. Right? And we want to find an integrating factor that's going to help us do some cool things on the left side of the equation here. So we want to find I of x such that the derivative of I of x is going to equal this right here. Right? If we can find this function I such that the derivative is itself times the function p of x, then I can rewrite this guy as I of x, the function of x times y prime, plus, well, I'm going to replace this with I prime, y equals I of x, q of x. So I didn't tell you how we're going to find it yet, but this is our goal, is to find a function I such that its derivative is going to be itself times that function. Now, if you notice here, this is just the reverse of the product rule. The left-hand side is just the function I of x times y derivative. The first times the derivative of the second plus the derivative of the first times the second is equal to I of x, q of x. So if we can find a function whose derivative is itself times p, multiply through, we can rewrite the left-hand side like this, and then we're going to integrate the left-hand side, and we'll integrate the right-hand side. But the antiderivative of a derivative is just itself. And we can't do anything further here. Yes, I'm just being sloppy with my notation for demonstration purposes. So then now we can divide by this magical function that we're going to find. So here we have a template for the solution to this differential equation. We can find this magical function I such that the derivative of I is itself times p, then we have a template for the solution. So how can we find I? What is this magical function? How can we find, oops, how can we find this function, I of x? Well, keep in mind, we want I of x times p of x to equal I prime of x, right? That's what we said, because then nice things will happen. So I'm going to rewrite this as p of x is equal to the derivative of this function that we're looking for all over the function itself. I just divided the I of x out from both sides. But notice that this is just, ready? I'm working in reverse here. This is just, this left-hand side right here is just the natural log of the function of I of x, the derivative. Because the derivative of the natural log of anything is 1 over itself times the derivative of what's inside. So we're looking for a function that follows these properties. So this is so cool. So we're trying to find I of x such that I times p is equal to the derivative of I, or in other words, the derivative of I over itself is equal to p. But this is just the natural log of the function that we're looking for. Well, why am I doing that? Well, now I'm going to integrate both sides. The antiderivative of p of x is the antiderivative of the natural log of I of x. It's derivative. But the integral of a derivative is just the function itself. So we can't do anything over here because we don't know anything about p of x, but this is just the natural log of this function, I of x. So we're so close for finding a template for I. So the antiderivative of p, which is found in this form of the equation, if we can find the antiderivative of p, it's just equal to the natural log of I of x. Well, to solve for I of x, I'm going to make these both the powers on the natural exponential function. So e to the power of the integral of p of x is e to the power of the natural log of I of x. But e to the natural log of anything is itself. So therefore, e to the integral of p of x is equal to this magical function that we're looking for. So this magical function we are going to call our integration factor, or our integrating factor. And once we have this, we're going to do this whole process. We're going to multiply it through, and then we're going to combine, and then we're going to multiply it through, and then we are going to rewrite it as a derivative of a product, and then we're going to integrate both sides, and really neat things happen. So if you're like, whoa, wait, bear with me, this is really super cool. All right, so let's just write down the steps. And it's better to do the steps and understand the logic behind them than to try to memorize the template. So given a first order linear differential equation, we want to make sure we put it in the correct form. If you can't put it in this form, then you cannot solve it this way. Put your DE in the correct form. We need the derivative of the unknown function plus some function of x times the unknown function y equals some function of just exclusively x on the right-hand side. We want to find our integrating factor. And to find the integrating factor, you do e to the integral of whatever function's here tagged on to the y. So then we multiply. Multiply both sides of the differential equation in its proper form by your integrating factor. We're going to rewrite the left-hand side as your integrating factor. Yeah, let's call this I of x here. So then we're going to rewrite it as your integrating factor times the unknown function y. And then we're going to integrate both sides. And then we're going to solve for y. All right, so let's put these steps into action. I think these problems are so cool. All right, so go ahead. Pause it if you need to, if you're still writing. All right, so moving right along. All right, now remember, it has to be in this form in order to use this process. So we have to put our differential equation into the correct form. It has to be y prime plus p, some function of x times y. So let's bring this over to the left side, and we're going to call this x squared y prime plus 2y equals 0. All right, but I need y prime by itself, so now I'm going to divide everything through by x squared. So this is equivalent to y prime plus 2 over x squared, y. And if I divide 0 by x squared, I'm still just at 0. So now this is in the perfect form that we can do this process. So this is my function p of x. So notice it's a function of just x times the unknown function y. And this is my function q of x. And q of x can be constant. As long as there's no y's over there, we're good. All right, so our first step is to put it into the correct form. Our second step is to find our integrating factor. So I'm going to take this in order to find my integrating factor. It's going to be e to the power of 2 over x squared dx. So we want to integrate 2 over x squared. So I'm going to do that down here. Little side note. Antiderivative of 2 over x squared dx is equal to 2x to the negative 2 dx, right? Which is 2, let me add 1, so it's going to be what? Negative 2x to the negative 1. And I'll rewrite it like this, right? So this is equal to e, and the antiderivative is negative 2 over x. So that's going to be the magic function that we're going to multiply both sides. Now we have to multiply both sides when it's written in its correct form. We can't do it up here, it won't work. We have to do it down here. So I'm going to now take this, I'm going to multiply both sides of this linear first order differential equation by the integrating factor. Here's my integrating factor. So I'm going to have e to the negative 2 over x times y prime plus e to the negative 2 over x times 2 over x squared y. Now we like this because when I multiply the right hand side, I'm just working with 0. So it's pretty simple. Don't let the 0 make this complicated for you. All right, now notice that we have a function here and its derivative here. The derivative of e to the negative 2 over x is e to the negative 2 over x times 2 over x squared. So this function's derivative is just this. And then we have a function here and its derivative here. So this is just the reverse of the product rule. I can combine these into one and call this e to the negative 2 over x times y prime equals 0. And double check. It's the first times the derivative of the second plus the derivative of the first times the second. So this is perfect. Once we have this into this written form, the integrating factor times the functions and that whole thing's derivative, now we can integrate both sides. So now I can do the integral of e to the negative 2x y prime dx is equal to the integral of the constant. Well, the integral of a derivative, they just undo each other. This is just the integrand. And the antiderivative of a constant, the antiderivative of 0, is just a random constant, arbitrary constant. So notice I didn't put the arbitrary constant on the left side. I just kept it on the right because if I had two constants, I would bring one over to the other side and combine it to make it one arbitrary constant anyway. All right, now solve it for y. So if we solve for y, we're going to just divide out e to the negative 2 over x e to the negative 2 over x, and then we get y is equal to, well, a constant over e to a negative power. The negative power brings it up to the numerator. There is the general solution to the differential equation, x squared times y prime equals negative 2y. General solution. Remember, our original problem was x squared y prime equals negative 2y. To do, check this. This is what's great about differential equations. You can always check your answers. So if you took the derivative of this, don't forget you'd have to use the chain rule. It would just be c times e to the negative 2x times the derivative of negative 2x, multiply it by x squared, and then just take negative 2 and multiply it by the answer, and they should balance out. It should be the same on both sides. So I'll let you do that as a check. All right, let's try another one. This time we're going to solve an initial value problem. So not only are we given a differential equation, but we're giving an initial condition. So once we have our general equation, we'll plug in 1 for x, set the it equal to an output of 1/2, and find the particular solution. All right, so here's my differential equation. We'll worry about the initial condition later. X times y prime plus 2y equals x squared minus x plus 1. Now remember, we have to get it into the form y prime plus a function times y, so forth and so on. So we need to get rid of this x. So we're going to divide both sides by this in front of the x. We want the y prime standing by itself. So then I'm going to have y prime plus 2 over x y equals, now make sure you divide each term on the right hand side by x, x minus 1 plus 1 over x. Now that it's in the correct form, here's my function p of x. And then this is a function entirely with x's, has to only be x's on that side to the equation. So now we can find my integrating factor. My integrating factor is going to be e to the antiderivative of 2 over x dx. Right, now notice x is positive, so the antiderivative of 2 over x is technically 2 times the natural log of the absolute value of x, but because we are only working with positive x's, this is just going to be 2 natural log of x. Okay. All right, so now we can simplify this. This is just e to the natural log of x squared. Coefficients in front of logs can be put as powers of what's inside the log. And now the e and the natural log cancel out, so my integrating factor is just x squared. So therefore, we're going to go to our differential equation written in its proper form. Remember, it doesn't work if you do it up here to the original. We have to, once it's in our proper form, we find the integrating factor. We're going to multiply this differential equation on both sides by x squared. So we're going to get x squared y prime plus x squared times 2 over xy equals x squared times each of these will be x cubed minus x squared, and then x squared times 1 over x would just be plus x. All right, so close. We're getting there. We are getting there. All right, I'm just going to clean this up a little bit. I should have done that right away. This is x squared y prime. X squared times 2 over x is just 2x. Y equals x cubed minus x squared plus x. Right, notice here we have a function and its derivative. Here's the other function and its derivative. So this is just the reverse of the product rule. So I can write x squared y prime plus 2x times y as x squared y, the whole thing's derivative, equals x cubed minus x squared plus x. So now that we have it in this form, we can integrate both sides. X cubed minus x squared plus x. The antiderivative of a derivative is just the integrand. So x squared y is equal to, now let's integrate the right-hand side. Antiderivative of x cubed, 1/4 x to the 4th, minus 1/3 x cubed, plus 1/2 x squared, and we put our integration constant over on the right side. Now to solve for y, I'm going to divide both sides by x squared. So our general solution will be y equals 1/4 x squared minus 1/3 x plus 1/2. Now be careful here, we still have this constant c over x squared. Now we have to go back to the beginning and use our initial condition right here. We're told when we put in 1 for the input, the output is 1/2. So if I put 1 in for my input, I get 1/4, 1 squared, which is 1, minus 1/3 times 1, plus just the constant 1/2, plus c over 1, and I'm told that has to equal 1/2. We do the math, subtract 1/4, add 1/3, subtract 1/2, we get c equals 1/12. Therefore, my solution to this differential equation is y equals 1/4 x squared minus 1/3 x plus 1/2 plus, well, 1/12 over x squared is 1/12 x squared. And don't forget, you can go back and check. This was the original problem. X times the derivative of this plus 2 times this itself should simplify nicely to x squared minus x plus 1. So I'll leave that for you as a check. Okay, I've got 2 more problems here, so let's see what we can do with these guys. So solving the differential equation is not hard. The hardest part is just, making sure that you're good and strong on your integration skills and your algebra skills. All right, here we have y prime plus 1 over y, x times y equals the sine of x. So this is already in a beautiful form for us. This is initial value problem. We're given a condition, so our final answer will not have an arbitrary constant in it. So this is in our perfect form. Here's my function p of x, which we're going to use to find the integrating factor. Here is just the function of x all by itself on the right-hand side of the equation. So let's find my integrating factor. My integrating factor is e to the integral of p of x. Right, again, keep this in mind. These conditions are important because the antiderivative of 1 over x is the natural log of the absolute value of x, but because we're only working for x greater than 0, we can go with just the natural log of x, and e to the natural log of x simplifies nicely down to x. So my integrating factor is just simply the function